Hi everyone, it's Mrs. Meehan, and in this lesson, this screencast, I'm going to introduce you to our new unit, dynamics, as well as go over Newton's first law of motion. So let's start with a little history lesson here. So in our experience, objects must be pushed in order to keep moving. This is just what we observe. If you push a book across a table, eventually it's going to stop. It won't just keep going. What this means is that a force would be needed to have a constant velocity. This is what Aristotle claimed in his series of books entitled Physics, written 2,400 years ago. So fun fact, the first physics textbooks were written 2,400 years ago. Galileo thought a little differently though. So 400 years ago, Galileo proposed the following thought experiment, which revealed another perspective. So he was able to imagine a perfectly smooth surface. So let's try to imagine this for ourselves, and to do this I'm going to show a little simulation here in a moment. But imagine that the ramps you are about to see are perfectly smooth. If you let a ball go at the top of one side, what will happen in each scenario? Take a moment to make a prediction. Okay, so let's check out this little PhET simulation here. I'm just going to keep it pretty simple. Let me go to the playground, make a little ramp. I'm going to try and make it equal on both sides here. So I'm going to set up the grid. I'll put both of these up at 6 here. Okay, so this is relatively equal. Now what I'm going to do next is I'm going to take this skater. I'm going to make this so it is frictionless. Friction does not exist in this world. And I'll also let you see the speed meter. So I'm going to take this skater. I'm going to position her at 4 meters here. So remember that prediction you made? Let's see if it's correct. So she's starting at 4 meters and she's ending up back at 4 meters. So when you let go on one side, in the case where there is 0 friction, the object will rise to the same height on the opposite side. And of course, she'll keep going because there's no friction. All right, so let's restart the skater here. Oop. Now I'm going to set up a ramp. Let's say we make this a little more uneven. So we'll make this side a little less steep, but we'll keep the other side the same. What do you think will happen in this case? All right, let's put the skater again at 4 meters. And she goes right to 4 meters on the other side as well. So even though she's traveling more distance, she's still going to end up back at that same height on the other side. And again, this is where there's no friction. All right, now what's going to happen if I just lay this flat? All right, we can't see her anymore, but we can see her speed meter, and she is still going the same speed. She's going at a constant rate of speed here, and nothing is stopping her because of friction. Okay, so let's reflect on that for a moment. That is similar to the thought experiment that Galileo proposed about 400 years ago. So let's go take a look. So it's not that Aristotle was necessarily wrong. In everyday life, objects do need to keep being pushed in order to keep moving. So again, if you push a book across the table, when you stop pushing, it will stop moving. Aristotle is right in terms of what we see around us every day. But Galileo and later on Newton, who we'll see in a bit, they imagined a world where friction could be eliminated. So what friction actually is, and we'll look at this in more detail later in the unit, is it represents an external force acting on the object, just as your push is an external force. So in the absence of all external forces, an object's velocity remains constant. So two equal and opposite forces have the same effect, and they cancel to create a zero net force. So this brings us to Newton's first law of motion. So Galileo's observations were more fully formed in 1687 by the father of physics, Sir Isaac Newton, who called this observation the first law of motion. This law, the first law of motion, proposes that an object at rest remains at rest, and an object in motion remains in motion unless acted on by a net external force. In other words, an object maintains its velocity, both speed and direction, unless acted upon by a non-zero net force. Having zero velocity, being at rest, is not special. It is just one possible velocity, a velocity in which is no more special than any other. So it's still considered a velocity. This law is often referred to as the law of inertia. The word inertia comes from the Latin word iners, which means idle or lazy. Inertia is the tendency of an object to resist any change in motion. Let's take a moment to check out an experiment or a demonstration of a hard-boiled egg versus a raw egg. Okay, so in that demonstration, you would have seen that in the hard-boiled egg, it was more solid and acted as one. So when you did stop the egg, it stopped. However, the raw egg wasn't cooked and the liquid inside kept spinning even though you stopped the outside. So even though there was a net force on one part of the egg, it did not act on the inner part of the egg. Therefore, the inner part of the egg kept moving. Now, this brings us back to inertial reference frames. So, Newton's laws are only valid in inertial reference frames. An inertial reference frame is one which is not accelerating or rotating. It is an area in which every body remains in a state of rest unless acted upon by an external unbalanced force. When your car accelerates, it is not an inertial reference frame since the car is no longer at a constant velocity. This is why a drink on the dashboard of a car can suddenly seem to accelerate backwards without any force acting on it. The drink is not accelerating, it's standing still. The reference frame, the car, is accelerating underneath it. Let's take a look at a famous video about frames of reference. Okay. Let's try a couple practice problems. So in the absence of an external force, a moving object will... The correct answer is D. It will move with constant velocity. So remember, a force will cause an acceleration. If there's no force, there will be no acceleration, which means there is no change in velocity. So the velocity will be constant in this case. When the rocket engines on a spacecraft are suddenly turned off while traveling in empty space, the starship will... Again, the correct answer is D. It will move with constant velocity. So since the net force has been removed, there will be no acceleration. If there's no acceleration, that means that the velocity will now be constant. When you sit on a chair, the net external force on you is... The correct answer is 0. You're not going anywhere, you're not accelerating. If you're not accelerating, then there is no net external force acting on you. A rocket moves through empty space in a straight line with constant speed. It is far from the gravitational effect of any star or planet. Under these conditions, the force that must be applied to the rocket in order to sustain its motion is... The correct answer is D. You do not need to apply a force to sustain a constant motion or a constant velocity. A force would only impact the acceleration or a change in velocity. You're standing in a moving bus facing forward, and you suddenly fall forward. You can infer from this that the bus's velocity decreased. So when you are within the bus, you are moving along with it. So you are experiencing a velocity. The act of hitting the brakes is a force that is only acting on the bus. So the bus will experience a change in acceleration based on that. However, the force of the brakes did not act on you, so you will not experience a change in acceleration. Therefore, you will continue moving forward, just as the bus was previously. You're standing in a moving bus facing forward, and you suddenly move forward as the bus comes to an immediate stop. What force caused you to move forward? In this case, no force caused you to fall forward. You simply kept moving because no force acted on you to change your acceleration. The force only acted on the bus to make it come to a sudden stop. Therefore, only the bus's acceleration was impacted. Okay, for further practice, what you should do is complete the multiple choice problems posted to Google Classroom, numbers 1 through 11. Let me know if you have any questions.